Okay, I think it's already about 2 o'clock. Welcome. Again, welcome. Thank you for joining this roundtable. And my name is Yong-Hoon Jung of KAIST, Department of Nuclear and Quantum Engineering. And currently I'm doing a small project to develop small modular reactor funded by the Circle Foundation, 동그라미재단. It's funded by the Dr. 철수한. You met him yesterday. He delivered the keynote after the lunch. I wanted to introduce current activities in Korea, include KAIST, about the SMRs, and we want to have a chance to talk about the potential future collaboration to develop and deploy the SMRs in Korea, in US, in the world. Welcome again, and Dr. Yim, welcome. I think you met him already in Cali, right? Yeah. You have the seat. And welcome, Florence, and all the delegates from the US. And, the fourth session will be the introduction of small modular reactor activities in Korea. And second will be moderated by Florence. It's a roundtable discussion about the collaboration. Before moving into the first session, I'd like to give a chance for Florence to say something.
Thank you very much for hosting our delegation. It's great to be here at KAIST. It's a beautiful campus, and many of you are KAIST grads. So thanks for hosting us. And we had a very successful program yesterday. We talked a lot about SMRs and how two nations can collaborate on SMR development as well as an export area. So this is a very timely topic, and really appreciate for Professor Chung for inviting us here to learn more about Korea's program and how we can work together on the U.S. side. Thank you. Do you want to speak?
Okay. Before starting the session, I'd like to invite you to take a photo. 한번 나오시죠.
So, 우린 앉아 있으면
네, 앞에 가지고 앉아.
Okay. So,
옆으로 앉으시고.
just come around. Then we'll take a group photo.
So those at the bottom that can stay sitting, or what?
Yeah, here. Come sit here. Oh. Tall person needs to sit.
이건 맞겠네요. 여기 앉으라는 얼굴에. 얼굴이 동그란데. That's it. We need a skinning guy. There you go. Gary, 옆에서 이렇게 쳐야 되겠네. Sitting there.
You look very thoughtful here.
No, I'm balancing it out now. We're thinking about SMRs.
Okay, so let me take the picture. 1, 2, 3. Say cheese.
Okay. Thank you. Thank you.
Thank you.
Go ahead.
We don't want to do
Hang on.
You lazy.
Those Canadians are always tripping up the water.
There we go. The wheels are very nice on this. They move smoothly. It's just
Yeah,
there's
it does, doesn't it?
새로 생긴
stuff on the floor.
손호 교수님을 만날 게 만족이지 안 그랬으면 엄청 헤맸어요. 복도에서 만났어 진짜 몇 년 만에. 진짜 몇 년 만에.
Okay, let's begin the first session, the small modular reactor development in Korea. We have 3 speakers today. The first is Dr. Han-Moon Kim. He's a current director of Central Research Institute of KHNP, Korea Hydro and Nuclear Power Corporation. he is the responsible person for the innovative SMR development in Korea. Okay, let's invite Han Hong Kim.
직함이 프레지던트가.
No, you're too tall.
제가 뒤에 타고
예.
Good afternoon. My name is Han Hong Kim from Central Research Institute of Korea Hydro and Nuclear Power Company. Today I'd like to present the plan for the development of innovative small modular reactor in Korea. This is the near-term strategy for the export of nuclear power plants in Korea. For the well-prepared market, such as USA and Western Europe, we've got the US NRC design certification and the EUR certification for APR 1400. For newcomer countries which want a relatively small-sized PWR, we've developed APR 1000 plus, downsized from APR plus. APR plus is 1500 megawatt electric, Gen 3 plus PWR, strengthened passive safety system. For the special market, such as isolated area, we've developed 100 megawatt electric small reactor, SMART. Now we are on the licensing to get the standard design approval. What will happen in the future energy market? I think the keywords for future energy market are safety of nuclear power plants and the carbon neutrality and the harmonization with the renewables. And to resolve these issues, we need small modular reactor. Nuclear power can be one of the major candidates to achieve 2050 carbon neutrality because nuclear power plant does not emit carbon dioxide. However, nuclear power should resolve two issues, safety issue and the flexibility issue. After Fukushima accident, the safety is more important measure to accommodate nuclear power for the public. SMR can be achieved inherent safety by using passive safety features. So we can eliminate emergency flaring zone and we can eliminate severe accident. The other issue is flexibility. Nuclear power plant should be flexible to compensate the intermittent problem of renewable energies. SMR can be more flexible compared to large commercial PWR. These are the main reasons why many vendors want to develop the SMR. These are SMR market focused by UK and Canada. Many countries want SMR for various needs, such as electricity for remote area and the steam supply for heavy industry and power for mines. However, the major market for SMR is on-grid market to replace old coal plant. Many people agree and believe the coal plant must be retired to achieve carbon neutrality. So we are targeting this market. This market has some characteristics. First one, the plant size is flexible and limited. In general, old coal plants has 150 to 600 megawatt electric power size. So large size PWR cannot enter this market. And the power size should be flexible according to the buyer's order. And the second one, this market is relatively easy to enter, easy to build nuclear power plant because the old coal plant has already built-in grid, infrastructure, and site. Third one is that these sites are relatively closer to populated area compared to the nuclear power plant site. So the safety and the public acceptance of SMR are more important. In summary, I'm sure SMR is the best option to replace old coal plant. Because of a bright prospect on the SMR, many countries are developing many SMRs. Total 71 SMRs are under development. 17 by USA, 17 by Russia, 8 by China, and so on. Many SMR are, however, on the conceptual design stage. Currently, I think 4 or 5 SMRs can be realized into the market in near term, including Smart by Korea, and the USK by USA, and so on. As you know, Smart got the standard design approval by Korean regulatory body at 2012. And the USK got the design certification in 2020. The current Smart under licensing review is the updated version of Smart, strengthening passive safety features. As they still have some technical and economical problem to construct real plant. It means that it is not too late, although we start to develop innovative SMR right now, because we can build a nuclear power plant on time and on budget. ISMR is basically module type PWR. Reactor core, steam generator, CDM, and ICP and pressurizer are encapsulated in cylindrical vessel. The vessel is located in the compact steel containment. For the economics, we adopted ICP. To make forced convection during normal operation. After the reactor trip, however, pure cooling is done by natural force only, such as gravity, condensation, and natural circulation. This single module generates 170 megawatt electric, and a plant is composed of 4 reactor modules. So a plant generates 640 megawatt as a standard design. This is a milestone of the development of ISMR. We will finish the standard design by 2026, and the performance demonstration and the design certification will be done by 2028. So after 2028, we will ready for construction of first unit. This is a bird's-eye view of ISMR. Until now, we have focused on function, safety, and licensing of nuclear power plant when we developed the nuclear power plants. No one think about the outer shape. Now it's changed. It is important to give comfortable feeling to the public, because ISMR can be built near the populated area. So this bird's-eye view is made by collaboration with the engineers and artists at the conceptual design stage. This view represents the image of Korean national flag. The target of safety is to practically eliminate the severe accidents. So we do not need to evacuate people. This goal can be achieved by the adoption of a passive safety concept. We do not use any active components during all circumstances of abnormal situations, including severe accidents. So we do not require safety-grade external electricity. This is the example of passive safety system of ISMR. all non-local accidents are mitigated by the passive auxiliary feedwater system. This system consists heat exchanger and a valve to activate the system. This system is connected to the secondary side of the steam generator. When a valve is open, decay heat is removed by condensation and gravity. For small break loca, decay heat is removed by the heat transfer between reactor vessel and steel containment and outer pool. Large break loca is eliminated because the large pipe are not exist in ISMR. I think the safety goal of ISMR is relatively easier to meet compared to the economic goal. The most critical factor of ISMR success is whether we can meet economic goal or not. The target of the economics of ISMR is to meet LCOE as much as $65 per megawatt hour. Until now, we have claimed economy of scale. Larger is cheaper. So in Korea, the first unit, Korea Unit 1, is 600 megawatt electric. The recent nuclear power plant, APR 1400, is 1400 megawatt electric. The reason is well known. The number of components and the systems and the operating cost, including the operating steps, are not significantly different from the power. In this situation, how can you achieve the economics of ISMR? We need innovation. We have to simplify system, structure, and components, minimization of site boundary, minimization of construction costs, and the minimization of operating costs. To meet these goals, we need various kinds of innovative technologies, such as sharp fabrication, land transportation, artificial intelligence, remote control, and so on. The major candidate energy sources for 2050 carbon neutrality are nuclear and renewables. If both energy expand their portions, nuclear power should compensate the intermittent power generation of renewable energy. There are two options. One is automatic load follow operation, and the other one is excess energy storage, such as hydrogen generation or district heating, and so on. SMR is easier to adopt these options compared to large-sized PWR. Yeah, these are partial requirements of innovative SMR. Electric power is 170 megawatt electric. Core damage frequency is 10 to the negative 9 per reactor year. 10 to the 9 per reactor year means practically zero. LCOE will be $65 per megawatt hour, comparable with the large-sized commercial PWR. Operating steps should be less than 3 persons, and so on. I hope we develop innovative SMR on time. If then SMR can be the major nuclear power plant to contribute 2050 carbon neutrality. Thank you for listening to my presentation.
Okay, thank you, President Kim. And if you have any short question, one or two, then we can accommodate it in the.
In one of your slides, you mentioned that
You can use the microphone.
in one of your slides, let's try it a third time. In one of your slides, you mentioned that construction would start in 2028. So when will you expect commercial operation for that reactor, and where would the demonstration site be?
Yeah, our government policies changed recently. So before until last year, we cannot have the plant build the nuclear power plant in Korea. But government policies changed, so we have to set up the plant now, from now. So maybe this year or next year, we can determine where to build the first unit of the SMR.
Is Kerry new place? Is potential site for SMR?
Could be. It will be a last resort, I think.
in Gyeongju?
Yeah.
In Gyeongju.
Well, let me explain this our schedule. We have some regulatory issues to build. Well, technically our target is build one module in 2 years. In 2 years. Okay. And for whole one set, I mean 4 modules, is our target is we will construct in 3 years. And the problem is we don't have any combined license. So once we got the standard design approval, and we should start construction license again in Korean regulatory systems. So we have some discussions to, improve those regulatory systems, like the United States. You have these 2 different tracks, like the constructions and operation license, or you can get some standard design approval with this early site permit, and you can combine those licenses. If we get those new regulatory systems, probably we can build. Our idea is during our development for this standard design approval, we will find out some candidate site and we start early site permit. Then we can combine, if we have those core systems, then we can build as quick as possible. So probably early or 30s, we hope so. That's our target. And this is my personal idea. It's not determined yet.
Okay, thank you, President Kim. Our next speaker is Dr. Sang-ji Kim. 조용히 계시면
Doesn't matter, it's okay.
Okay, let's move to Professor Yong-hee Kim. He will talk about the current activities of developing SMRs, mainly by KAIST. Let's welcome Professor Kim.
Thank you. Thank you. Okay, thank you. Well, welcome again. So I think I have maybe 15 minutes or 20 minutes for this
That's fine.
discussion.
20 minutes would be fine.
Okay, thank you. So I will briefly present to you about ongoing SMR researches at KAIST, right here. So this is the content. I will briefly discuss our water-cooled SMR, which is some different from the KHM-based ISMR, but should be quite similar. And nowadays, we are also focusing on quite, in a sense, crazy, but very advanced molten salt reactor SMRs, several kinds. So I will very briefly introduce some key ideas of the molten salt-based SMRs. And then I understand that you are mostly about the policies. So I'm trying to propose a possibly interesting, sustainable nuclear fuel cycle. This is just an idea. And then some collaboration topics. Minute ago, so Dr. Kim, he introduced their idea about the innovative SMR by KHNP. Actually, about 7 years ago, we began this project, so-called so research project, government-funded research project to develop autonomous SMR. So 7 years ago, when I talked to KHN people about SMR, they say this way, oh, it's nothing, don't do that. But looks like now they are crazy about SMRs. Everybody's talking about SMR. So again, 7 years ago, we began this sort of pathfinding research activities. Interestingly, our goal is to design a soluble boron-free SMR. The soluble boron is a very, very important sort of way to control the reactivity in the commercial reactors. But it has many problems. So what we're trying to eliminate, completely eliminate the soluble boron. And that is the same goal with the ISMR, with KHNP. And we also, so to come up with a very nice and competitive, SMR, we devised a new lattice, so the pure assembly lattice, which is named here truly optimized PWR, or shortly TOP. So this year we have almost nice view of the reactor cores, which has 69 pure assemblies and 2 to 5 year cycle lengths, and providing about 45 or 50 gigawatt day. But this is quite high compared with the big size ones. So let me show you. One of the very intriguing capability of this soluble boron-free SMR or atom is this passively autonomous load follow. She can do load follow in a very beautiful way, so my demand is changing. But we don't do any control. We don't do any control in the primary or in the reactor core. Nevertheless, we follow the demand almost perfectly. This is all due to the inherent feedback mechanism. That's why I call this passively autonomous load follow. Now, let me talk about some advanced research activities for the molten salt reactor type SMRs. We are looking into quite different molten salt reactors. This is the very familiar thermal spectrum Gen4 type schematic. We don't go this way because it has many problems. Instead, we will go to the fast spectrum molten salt reactor, and you may remember that Power and European countries, they are looking into that way. Why molten salt reactors? We understand the CBS that could be almost completely eliminated using these molten salt reactors. In addition, there is no accumulation of spent fuels, which is biggest hurdle or biggest problem in the nuclear industry. So it looks wonderful. Nevertheless, there are many challenges. That's why we don't have the MSR yet. Just like in the US and European approaches, we are looking into quite different molten salt fuel, which is so-called chloride, not fluoride. But we also trying to have some quite interesting fluoride fuel, based on the sodium fluoride, potassium chloride, and uranium fluoride. So we have a few MSRs. This is the first one, which is under development in university. So in collaboration with the other universities, Hanyang and Gachon University. Unlike many other MSRs, this is natural circulation MSR, maybe the only one nowadays in the world. And we have some nice concept to cool the about several hundred megawatt thermal MSR using just a natural circulation. And so we are doing a lot of analysis to devise some nice reactors and systems, and this is about the safety. So the temperature coefficient is very strongly negative, and this is very wonderful in many ways. And see, as you see here, this is very preliminary thermal hydrogen analysis showing the natural circulation of the molten salt fuel itself. But again, this is very preliminary, and our research indicates we can achieve passive safety using just an air cooling without any active systems up to about 400 megawatt or so. So that means maybe 150 megawatt electricity could be produced in the single unit. And another one. Now this is KAIST activity. I mean, in our department only. The PI of this project is Professor Chung Yong-hun. I am looking into the reactor cores. So this is forced convection MSR. So we do use PERP. And we're going to use, again, the chloride fuels. And this is going to be long life MSR. So once we load nuclear fuels, it can be utilized over 20 years without any refueling, any feeding, any online treatment. So we don't do any online reprocessing, any online treatment. So I believe this can be truly proliferation resistant. Again, with this MSRs, the wonderful passive load follow operation is very, very easily done. That is one of the very nice attributes of the MSR. Another one we are looking into here in KAIST is very ultra small, extremely small and very long life. I call it molten salt and metallic reactor. This is very unique. So here we have a reactor vessel, and right here at the bottom we have a metallic fuel, so uranium ion. And above this liquid metal we have molten salt. The molten salt is coolants, and most of them are naturally driven. And then it can be extremely small, like the diameter only about 60 centimeters, but we don't need very high enrichment. The necessary enrichment is only 12%, not 20%. And then the lifetime almost indefinite. And this is what we got from the neutronic analysis. So we need only about 2 tons of 12 enriched helium. Now, let me propose one possibly truly sustainable fuel cycle. I believe in US and in Korea, one of the pressing, urgent tasks is to deal with spent nuclear fuel. And we are developing pilot processing to recover TRUs, transuranics, but that is dirty TRU, as you understand. And these TRUs will be burned in the molten salt reactor without any additional pilot process. In the conventional pilot processing we propose, we do again pilot processing because the burnup of the TR is rather small. But here in the molten salt reactor, almost 100% the burnup or utilization is theoretically possible. So I believe this is the very ideal combination. I mean, the pilot processing and MSR. So from the pilot processing, fission products are removed, and then some of the short living but quite radioactive, for example, strontium-90 and cesium-137, that will be possibly just stored. And then most of the short lived go to the repository. And here, I'm proposing a very new and very intriguing idea to deal with these long-lived fission products. So they have lives over 1 million years, maybe 10,000 years, and I found that they can be treated in a very, very interesting, unique way with so-called bound state beta decay. You're not technical person, I believe, but let me tell you this. See, cesium-135 and iodine-129, technetium-99, these are most problematic long-lived fission products. If we can deal with this nicely, I think we don't worry about fission product from the nuclear fuels. Problem is, they have lives over 1 million years. However, if we remove all the electrons from this neutral atom, look at this. This is a theoretically estimated half-life when electrons are all removed, less than 1 year.
How do you do that?
Good question. People are doing already this with a small amount, but nobody look into this kind of trend. So I propose people are doing this in a high physics laboratory, but no nuclear industry people, we are not aware of this kind of physics here, surprisingly. That's why I'm talking to you. Anyhow, this is not easy. So it's a last slide. I believe in the advanced reactor developments, the nuclear fuel, that is the most maybe urgent and most difficult and important issue in Korea and in the US, the HALO. How to secure the HALO fuel. Well, the Russian-Ukraine war. So maybe as somebody proposed in the US as well, pilot process, proliferation resistance, pilot processing of NWR stockpile, probably one possible option. Again, just probably one possible option. Another issue or problem we have with SMRs and current LWR plate is to maximize the discharge volume, to minimize the spent fuel volume. For that, we need to increase enrichments for the commercial LWR just slightly, like up to 6 to 7%. But this is not also easy. I think we need collaboration for this kind of HALO and also slightly over 5% enrichments between US and Korea. Regarding the molten salt reactor research, you are doing very seriously on the molten chloride salt reactors. Unfortunately, we are not collaborating with the US. We do hope, but looks like they really don't want Korea to join the activities. We do hope, and hopefully we can discuss how we collaborate for the molten salt reactor development in both US and Korea. And lastly, I think the licensing process, maybe this is the biggest hurdle for the developments for the advanced reactors. So I hope we can also discuss some collaboration between US and Korea in this area. So let me stop over here. So yeah, that is my
Can you go back to your flow sheet?
which
The 2 slides now.
first slide.
Yeah.
Yes.
No, one more.
One more.
So let me ask,
All right, so you're going to take spent fuel and you run through power processing. You have a dotted line for the uranium, 98%,
Yeah.
which is essentially the bulk of the material stripped out by pyro. What's the dotted line mean?
So, this is not the latest project. If necessary, uranium can be utilized as a fuel. Again, if necessary. If we just try to transmit or incinerate TIUs, we don't need any more uranium. But again, in a sustainable nuclear fuel cycle, maybe you can reutilize the uranium.
So you would contemplate the uranium for a breeding cycle? Is that
Not
right?
really breeding, just a break even.
Oh, okay.
Break even. Yeah.
And can you go back to this decay idea of?
You mean this one?
Yeah.
Yeah.
In order to achieve that kind of stripping, you would have to have a cyclotron to do that. I mean, there's not enough energy in a reactor, so you're going to have to accelerate this. I assume through a cyclotron, a LINAC. Well, I'm not sure even a LINAC would have the energy to do that. But I'm just curious. So, what's the concept here? How would you? You can strip out iodine, you can strip out the Tech 99, but then what? And by the way, that chemical processing is difficult.
Okay.
So I'm curious to say how you would ultimately achieve the energies that you would need to strip this out.
It's surprising you raised such a difficult, physics question. Let me answer very briefly because of the time. See, in the current high physics laboratory, they utilize in very, very costly way to remove electrons from neutral atom. But we have to remember the total binding energy of electrons, for example, in cesium atom, only about 200 kiloelectrons. For the iodine, 195 kiloelectron. For technetium 99, 111 something. So if you think about actual total binding energy of electron, there could be much, much better way. I have a few ideas. So we may communicate after this discussion.
All right,
Thank you.
that's fair. Thank you.
Thank you.
Any more questions?
Okay, thank you. Thank you, Mr. Kim. Next speaker is Dr. Sang-ji Kim of Kerry. He will talk about the current status about molten salt reactor development. He has a very large quantity of high quality of experience on PWR, lead-cooled fast reactor, sodium-cooled fast reactor,
And molten salt cooled fast reactors.
That's a security policy of Kerry. Once you use the USB sticks from the Kerry, you need that kind of thing. Sometimes it doesn't work.
Yes, we've been in meetings like that.
Yeah.
Oh, you have to say antivirus software?
They some crazy software.
You have to download the security program.
Yeah, there's that kinds of things. I have no idea. The only thing I know is it's half and half. Sometimes it works, other times you can't.
Security.
It's very frustrating. It's a very creative way of secure those data.
So, keep the security by allowing nothing,
Yeah, that's right.
by doing nothing.
Technically impossible. 아니 저게 우리도 저거 뭐 엄청 먹자면 반출 절차에 뭐냐고 안 하고 말하고 그냥 메일로 보내면 되는데 왜 저것도 USB로 만들어줄까?
Okay, thank you for waiting at first. Due to the high secure customs in Cali, it always causes me trouble when I go out of Cali to make any sort of presentation. And also today we see that happen again. So today my talk is about the molten salt reactor status and projection at Cali site. So in the right side, you are looking at the Gyeongju site that is currently under construction. Maybe usable from 2025. And my hope is to locate one of my experimental reactor or prototype reactor at the front of this site. In the sea.
In the sea.
Yeah. So actually, I'm not going to locate the reactor on land, but in the sea. That's I draw two pictures. One is a container ship, and this is the FP. So I would like to see that those ships are serviced in the sea over that area. So the title starts with the projection. At first, I'm very much glad and very much delighted that excellent person like Professor Kim is a strong promoter of molten salt reactor in Korea. So I have a strong support from the academia at first, and because they are light compared with the KLE, Korea Atomic Energy Research Institute, they are quick in motion. They are quick in starting the new research. So that's the reason why I asked the Professor Kim to make a presentation earlier than me, so that his research status is ahead of me. So we are, in case of Kelly, we have a big inertia, so we are always late in making any new kind of project. So that's the reason why I titled as a projection on MSR. However, we have already an ongoing project started this year. That is a laboratory directed research project that started from the January of this year. I will talk about it in the next slide. The bigger one is coming from the next year. Actually, I proposed the national R&D program to the Korea Advanced Research Agents project. That happened in the January of the last year, and after severe competition of 140 candidates, actually my proposal was chosen as the #1 project among 140. So in the February of the last year, we went through the competition process and made presentations in front of the evaluation committee. Then there was a talk between Korea Atomic Energy Research Institute and the Ministry of Science to make a project for this. This is very important because in Korea, to have a long-term development program, we need to look at our project as a government-funded project. Then we can utilize that one. Otherwise, the program can be just 1 year long. So we want to register our project as a long-term R&D program supported by the government. So that is the effort going on this side. Unfortunately, it's still to be determined. We are still trying to secure the budget for the next year. But our project plan includes everything required for designing, construction, molten salt reactor. Not just the reactor physics, but also reactor system, all of the systems, including balance of plant, also the fuel qualification, and then monitoring and many physical property measurement studies. All set of researches to realize the MSR technology are going to be covered by our project. And on the right side, you see a schematic that I imagined when it is used in the ship. Actually, I want to use this reactor as an engine for the propulsion purpose. And long-term plans, it's still shaping. So this is not firm at all, not fixed at all. So it can change, and I don't have any responsibility. And that's important. So I did not say that we are going to follow this project plan. Okay, I have no responsibility and no, and I wish we could follow this process so that by 2026 or mid-2030s, I hope we have an operating reactor. But in my mind, I would like to accelerate this development. Maybe in the early 30s, I hope we have a prototype reactor so that can be deployed in the 2030s. So this is just a one-year project, and the reason I want this project to serve as a seed project for the future molten salt reactor key technology development. And also it enable just a jump start for the coming project. So you see that the reactor is placed in the ship. So the research goals and topics are classified into three disciplines. The first area is MSR enterprise key technology development, and the second area is about salt preparation and process key technology development. And then the third area is fuel qualification and salt monitoring technology development. So I'll briefly explain what is going on the three different areas. So at first, the MSR enterprise key technology area, we are currently studying the pure salt options, and then pure cycle length variation, and then nuclear evolution and distribution inside the reactor system, because it keeps changing already, because fuel is circulating all of the reactor systems, because it is leaking. And then we at first step, we want to establish computer code suites for system design and analysis. And we started the pre-conceptual design of main components. In addition to that, we also started some analysis on safety, and we are preparing safety design criteria and the system safety analysis computer code, and like ISMR, we also have relatively courageous, maybe bold loop. I want to show that the loop for our MSR will be as low as 10 to minus 13. Okay, so you saw that the ISMR is targeting 10 to minus 10. Okay, so I want to prove our log will be 10 to minus 13. And the reason is, as Professor Kim stated, the problematic isotopes upon the accidents are cesium, strontium, and iodine. Those are very important source terms upon accident. In case of molten salt reactor, chlorine, there are surplus chlorine inside the system. So it will combine with the cesium strontium. So it means that strontium and the cesium cannot go out of the molten salt. What is the reduced probability when it is captured inside the molten salt? It is 1 to 200,000. Okay? So if we can reduce the probability of salt spill below 10 to -7, then when I multiply another 200,000, then it will reach 10 to -30. So we can actually practically eliminate any severe accident that radioactive isotopes go out of the reactor containment. Okay, so that's the route that I would like to see from this reactor development. And another one is liquid fuel manufacturing and fission product management technology. So you see, we actually borrowed this figure. So basically, when it is solid on in the molten salt status, these dark. Actually, the fuel itself is brown and others are white. However, when we melt it all together, it is clear like this. So it is very easy to see what's happening inside the reactor. The more advantage is we don't need to look at inside in case of molten salt reactor because there is nothing there. In case of chloride molten salt reactor, there will be nothing. Only salt will be there. So because there is nothing inside the core, why do I need to do that? How do I need to see that? Because there is nothing. However, it has an added advantage of visibility in case of molten salt. And another one is technology development for thermophysical property evaluation and prediction. So we just started to, actually we had some capabilities to measure various properties such as density, then viscosity, heat conductivity, vapor pressures like that. And now we are integrating those technologies to identify or to measure the molten salt properties. So this is also going on. But all of these sea area projects are going to continue just for 1 year. So if we are successful in securing budget for the next year from the CARPA project, then we will continue to develop these technologies. And the R&D cooperation plan, so we have some made MOUs with Samsung Heavy Industry, and then another MOU with the Korea Research Institute of Ship and Ocean Engineering, KRISO. And then we also talking about the CRADA contract to have the thermophysical measurement of actinide bearing salts, because in Korea actually we cannot handle plutonium, americium, and curious sort of thing. So because of that, we are asking our INL friends to do some thermophysical property measurement works. And actually, I think this CRADA is now under review by the DOE, and I think we will pass the approval of DOE. I think we can get it. And then collaboration with MSR developments, including private companies, are always welcome. And I'll skip this. So there are more than almost 30 startups all over the world working on the molten salt reactor development. And so I want Kelly can play the role of providing the service to these molten salt reactor startups by having integral test facility in our Gyeongju site. So I'm going to build chloride and maybe chloride salt-cooled integral test loops in 3 or 4 years. So this is the areas for cooperation in developing MSRs. I think we are already running out of time. I'm not going to speak in detail, but VMV of MSR modeling and simulation and the component development like pump, freeze plug, valve, and material preparation. And let me see, compact efficient heat exchanger and the molten salt system monitoring that is used for process sense measurement and the system level material accounting, modeling, and simulation protocols. Actually, I asked all of my team members to find out some items for the cooperation. So I have almost 20 more pages for these areas. For each topic, I had a slide, but I removed it. But I would like to share my hope with you for the fourth item. That is a set of MSRP's critical experiments, and I want we can share data and budget if possible. And I am proposing 4 items. The first one is chloride salt-based zero power reactor physics experiment, and then low power experimental reactor design, construction, and operation is also possible. Another one is based on this zero power reactor physics experiment, we can create numerical reactor benchmark problem for the fuel reactor. And the fourth item is shielding experiment design and setting up of motor. So I would like to show you some of these ideas. Yeah, so yeah, I would like to set up a zero power reactor physics experimental, then low power experimental physics. However, my wishes are already coming true in the US. Actually, US DOE has an advanced reactor demonstration program, risk reduction program. So with that program, about $170 million was allotted for the operation of molten salt chloride reactor experiment. So this project already started from 2020, and they are expecting to have the operating reactor by the end of 2025. So if we can join this consortium, then I think it can be a great asset for validating our computer code, so that it will accelerate our licensing process pretty much. So I hope we can work on it, and so far our efforts was not successful. Actually, I contacted TerraPower and also made a talk with Core Power with the aid of Gavi, but there was just one discussion round, and that was handled. Okay, this is another one is a shielding experiment. Kerry has neutron generation facility to perform shielding experiment so that molten salt reactor shielding experiment can be done in the Kerry site, and we can set up some experiment and validation cases for any need from outside the Kerry, also for us. Okay, thank you very much for listening.
Thank you. Okay, I think we